In this video, we'll be looking at acid-base reactions. So for acid-base reactions, the first thing we need to do is write an equation, and we can look at our problem to tell what the reactants and products might be. In this problem, it says, what is the molarity of a 1 liter sample of H3PO4 if it requires 150, it's supposed to be 1.50 liters of a 0.100 molar CaOH2 solution to neutralize the sample. And so we can see here that it's talking about H3PO4 and CaOH2. So we've got our acid, which is H3PO4, which we can tell because it's got a hydrogen in the front. That's going to be our indicator of an acid. We've also got CaOH2, which has an OH on the back, which is our indicator for a base. In our reaction, we should have our acid plus our base, reactive form, our product, one of which is water, which is formed from the hydrogen on the acid and the hydroxide on the base. We can kind of think of water as HOH with that acidic hydrogen and then the OH from the base that have come together to form a compound. And this is really just a double replacement reaction. Our second product is going to be made from what's left after we've taken off the H and the OH. So we're going to have our Ca as the cation, and the PO4 is going to be the anion. Now, because neither of these have a +1 or a -1 charge, we do have to balance some charges here. Calcium should be +2 and phosphate should be -3. And that means that our charges here are actually going to crisscross and give us Ca3PO4 2 as our second product. From this, we can figure out what we're doing. In this problem, I'm only given information about one of the reactants that's going to be helpful. It's asking for information about the second reactant, so that means that this is just going to be a regular stoichiometry problem. If I'd have been given information about both our reactants and asked about one of the products, that would be limiting reactant, but that's definitely not what's happening here. So what we're going to do, we're going to take the information about our acid, or about our base, which is this 1.5 liters and the 0.1 molar solution, and we're going to find the number of moles because we have to have moles to start our stoichiometry problem. And so if we take the molarity equation and rearrange it to get moles by itself, moles are equal to molarity times liters. Here I have molarity and liters. I don't need to convert either of those, so I can just get started. In this problem, we can see that molarity is going to be 0.100 molar, and the volume is going to be 1.50 liters. And so if I go ahead and do this, I should get the number of moles of calcium hydroxide is actually going to be 0.150 moles of CaOH2. Once I have that, I can go ahead and set up my stoichiometry problem. In this case, what I'm going to have to find is the number of moles of my H3PO4, which I can tell because it's asking me for the molarity. The two things that are with molarity in the molarity equation are moles and liters. I have liters, I don't have moles, and so that's what I'm going to be needing. I'm just going to go ahead and take my 0.150 moles of CaOH2, and I'm going to make a fraction. Since I'm going from moles to moles, I only need the one fraction. One thing I did not do before, though, is balance my reaction, so I have to go back and do that. In my reaction, if I look here, I've got a little bit of a problem because I've got hydrogens and hydroxides, and it looks confusing. So in this case, it's really easier to treat my water as HOH and treat them as a hydrogen cation and hydroxide anion. That way I can still treat it as ions that I see exactly on one side and the other, because I see my hydrogen ion on both sides, I see my hydroxide on both sides, I see phosphate, and I see calcium, and they would all look identical. And that's going to help me with a lot because there's a lot of oxygen in this problem. The first thing I need to do is balance those calciums, and so the easiest way to do this is by adding a 3. I could start with the phosphates also, but I'm going to try to save the hydrogens and the oxygens for last because they have a water where they're both together. It's just going to be easiest for me. I'm actually going to choose to balance the phosphates first because that's going to make my hydrogens easier later. Looking at the hydrogens, I have 3 on one side and 2 on the other side. And I don't like that because they're both small numbers and one's even and one's odd. Generally, that means they're going to be difficult to balance. Now, looking at this, if I put a 2 in front of this H3PO4, that's going to give me 2 phosphates on each side. And that's going to give me 6 of my hydrogens that come from the acid. Remember, if we're treating water as HOH, that means we have 1 acidic hydrogen, 1 hydrogen that came from the acid, in each water molecule. And we need 6 of those total to balance out the one that was on the other side. So I'm just going to put a 6 here in front of this water. And that means I have 6 hydroxide ions also. On the other side of my reaction, in the reactants, I only have 2 of them. So I'm just going to put a 3 here in front of my CaOH2. Doing that actually goes ahead and balances my calcium, because now I have calcium, 3 on each side. And if I look, everything should be all balanced out. With that done, I can just head back and finish out my problem. I can fill in this problem by knowing that I have, in my balanced equation, 3 moles of CaOH2, and on top of my problem is going to need to be 2 moles of H3PO4. What that tells me is that for every 3 moles of my calcium hydroxide, I need 2 moles of my phosphoric acid to cancel that out, to neutralize it. And if I do the math here, I should be able to get an answer for the number of moles I have. I'm not done, but I'm getting closer. Whenever I type this in my calculator, what I'm going to get is 0.100 moles of H3PO4. And I always like it whenever I get nice even numbers like that, because it makes my math a lot easier later on. The last thing I need to do, I'm still not quite on my answer because it's asking me for molarity of the acid. I do have moles though, and molarity is equal to moles over liters. Got molarity, I've got liters, so I just need to put them in here. My moles are 0.100 moles of H3PO4, and my liters are 1.00 liters. And if I go ahead and divide those two, then my molarity is 0.100 molar H3PO4. And that's going to be my final answer.